So in this video, we're going to be talking about the natural exponential function. Now, when we mean by the natural exponential function, what we're really talking about, all right, is this number e. Now, e is approximately 2.71828 and a bunch of non-repeating decimals after that. Now, in the previous video, I also kind of gave you an indication of what e looks like defined. So, e, by definition, is equal to 1 plus 1 over n, all raised to the n power. Let me write that a little cleaner here. So if you let n get larger and larger and larger, so do like a little table here, 1 plus 1 over n, all raised to the n. So if we let n equal 1, we get 2. If we let n equal 10, we're going to get 2.59374. And like I said, if we let n get larger and larger, let's say n equals 10,000. Well, as soon as n equals 10,000, you get 2.71815. If n equals a million, you're going to get 2.71828. And as long as n gets larger and larger and larger, you will converge onto this number right here. And depending upon how many decimal places you need, that's how, I guess, large n is going to be. Or I'm sorry, that's how large e will get to in terms of decimal places themselves, okay? So there are a lot of different things that we use e for. For example, exponential growth, exponential decay, natural log, stuff like that. Even in geometry. So, like for example, the Gateway Arch, which is in St. Louis, is modeled off the equation y equals a times the quantity e to the bx plus e to the negative bx. And if you were to graph this archway with a equal to 1, you start to get that golden archway that looks like this, and it's in St. Louis. It's like the gateway to the west is what they call it. But it's really interesting that this letter E pops up everywhere in nature. It's like pi. It's so special that it got its own letter. So the person, I don't want to say solely responsible for E, but the person who really brought E to light is called Leonard Euler. Okay, it's not Euler, it's Euler. All right. And Euler was chosen probably because the first letter of his last name, or I'm sorry, the first letter of exponential started with E. So he chose E to be this special number. Okay. Now a simple definition. So the natural exponential function is nothing more than just f of x equals e to the x. In fact, you have this e to the x button on your calculator, and if you were just to evaluate f of 1 in your calculator, you would get approximately 2.7718, and depending upon how many decimal places your calculator will display, that's how many decimal places you will actually get. The graph of an exponential function, in this case e to the x, follows all the other ones. So since e is 2.7, it's a positive number. In other words, a is greater than 1. We know that it's going to creep along the x-axis when my x values are negative. And then it's going to cross the y-axis at the point 0, 1. And it just, when x gets larger and larger, the exponential itself is going to get larger and larger. So there's going to be a couple homework problems where it says like evaluate, like e to the third. And all you have to do is just type into your calculator e to the third. And your calculator should say something like 20.9 or 20.085 or something like that. I'm not really going to do too many of those examples because you can definitely see them. All right, just using your calculator. What I really want to go over would be continuously compounding growth. Okay, so in the previous section of the previous video, we looked at compounding growth in terms of the formula a equals p times 1 plus r over n, all raised to the nt. And we learned that if n is, let's say, annually, then n equals 1. If it's quarterly, it's 4. If it's weekly, it's 52. If it's daily, it's 365. But the question becomes, what about continuously? Okay, and that's where this E thing kicks in. So if you have 1 plus 1 over n all raised to the n, what you're going to do is you're going to replace that with the letter E. So continuously compounding growth sorry, I'm just writing this fast. Continuously compounding growth has this formula right here, and it's very simple. It's going to be A equals your principal times e to the RT. So it kind of makes our calculations a little bit easier. So then the question becomes, all right, well, what if you let P equal 10,000, R equal 8%, T equals 5 years, and you let your money continuously compound? How much money would you have at the end? Well, this would just be A equals 10,000 E to the 0.08 times 5. And you should get a total of $14,918.25. So the interest earned on this would just be $14,918.25 minus your initial investment of $10,000 for $4,918.25 of interest earned in 5 years at 8%, which is very good. I mean, if you can find an investment that pays 8%, definitely invest in that because it's pretty good. It's pretty good, especially for the current climate that we're living in right now. The last thing I kind of just want to go over real quick, it's very simple. It's just, what if we wanted to graph f of x equals e to the negative x? Well, I mean, there's two ways to look at this. You can kind of have an idea of what this is gonna look like, or what we could do is just rewrite this as 1 over e to the x. In other words, what I did is I applied my negative exponent rule, and then I just said, well, what I'm going to do is just rewrite this as 1 over e r raised to the x, because no matter 1 to the x is always going to be 1. It's the e to the x that we really got to be concerned with. So since this is 1 over e to the x, we're going to have that exponential decay. So once again, it's just going to come down this way and just creep along that y equals 0 asymptote. And this is going to be the point 0, 1 again. And like I said, this is going to be exponential decay. Now, in the next video, we're going to start talking about logarithmic functions. And logarithmic functions are the inverse functions of e to the x. In fact, let me go ahead and open this up real quick. So just to show you, and this, like I said, this just be like our little introduction. We have the line y equals x. I'm going to go ahead and just make this a dotted line. Now I'm going to go ahead and graph e to the x. Okay. Now the natural log of x, you're going to notice here, is a mirror image of e to the x. In fact, that's going to happen a lot for us when we're talking about exponentials versus their inverse logarithmic functions. Okay. So anyways, so this is just kind of like a teaser to what we're going to be going over. And I'll see you in the next video. Bye.